Action. Preparing the live stream. Now we're one time.
Victoria, do you want to close the door?
Yeah, so okay.
Okay, so we just use normal pointer. So now it's working.
This is strange.
No, I don't know. My stick was working.
I know.
Because usually, yeah,
There you go.
You can lose the mouse.
Very good. Okay. Are we ready?
There are still yeah, you have to write these people from doing. Yeah, the hybrid setting is always a bit challenging.
So welcome to everyone to this series of IFIMAC+ICMM series. Today it's my pleasure to present the speaker, Professor Christophe Galland. I'm a bit biased about Chris' achievements, but I think I'm objectively, they're objectively impressive. I'm gonna just do a summary. He studied his bachelor and master in the cold coding technique in Paris, specializing in solid state and quantum optics. Then he did his PhD in ETH Zurich with the group of Professor IFIMAC+ICMM, and he did some pioneer experiments on single photon emission in carbon nanotubes. I believe Professor Joachim Zanger and Gerald Feist was among the committee, right? In your job. It's interesting. Then he did several postdoctoral research space, as most of us had to do, in the US, in Los Alamos, and at the University of Delaware to work on nanocrystal quantum dots and integrated quantum optics. And then he moved in 2013 until nowadays to EPFL. First as a postdoctoral researcher in the group of Tobias Kippenberg to start developing what some of us will start to call the field of molecular optomechanics. And since 2017, he's leading his own lab, working mainly on molecular optomechanics and other nonlinear single photon phenomena. Among the many grants he has win, I want to emphasize the ERC consolidator grant that he got in 2019. And well, I had the opportunity to meet Christophe in a workshop in Mallorca where we approached and we started sharing some of our ideas on molecular optomechanics at that time. And this turned into a beautiful collaboration. That is why we met. And I think he's going to speak partially about this today. So I don't take more time. Please, the stage is yours. Thank you very much.
Thank you, Diego. Thank you so much for inviting me here. Even also fighting against all the administrative rules. It's very, very nice. The first time I mean, I've been to this campus once during my PhD for a conference. So the first time I had the opportunity to visit here. So it's I'm looking forward also to the discussions. Yes, so I'll be presenting some of our recent work in the past few years in my group in molecular optomechanics, which, you know, admittedly is only a name, as you probably know, which describes some aspect of Raman scattering, and in particular also what happens when molecules which can lead to Raman scattering are placed in plasmonic nanocavities, as in this picture. But the first part of my talk will be also about some more fundamental aspect of Raman scattering in free space. It's in bulk materials, which also shows some interesting quantum optical features. So one of the, so it's again not working. I don't know why it started to work or not. So now it works, but okay, I'm not far, so I can probably steer. Ah, no, but it's just that sometimes you want us to click again on this screen. So there you go. Okay, good. So yeah, one of the background is to yes, to consider whether phenomena are coherent or incoherent, as you know. And in the classical domains, you all have a good understanding of what are a set of, or what is coherence and not coherence for classical waves. And as you also know, probably you can translate these concepts to wave functions, to the quantum domain. And there things get a bit more interesting and also harder to picture. So for example, if you have an ensemble of molecules, if their wave functions are incoherent, it really means that each of them is living their own life. But if they start to share coherence in their wave function, we call this entanglements. And actually, I was looking a bit at this, what is the relationship between quantum coherence in general and entanglement, and these two papers seem to suggest that this is really the same thing. In fact, it's entanglement is a specific manifestation of quantum coherence. But I won't enter into these debates. I just wanted to say that these physical concepts are not only interesting to study, but they are leading to applications. And as you know, in the classical domain, classical coherence is being really instrumental to today's technology. It's because of that we can now broadcast this thing on Zoom or do all the things we do today, because we have coherent light source which can transmit much more information than incoherent light. And more recently, this is the second quantum revolution, we are also starting to use quantum coherence in new generations of computing or sensor instruments. And you see that here we can do very small things like lasers. Lasers can be as small as a nanopillar or something, even plasmonic lasers can be very small. To leverage quantum coherence, we have to be much more careful to shield the system of interest from its environment, which a bit paradoxically leads to much bigger machines. So you have to go to very low temperature or to be in ultra high vacuum, even though in the end you are studying single ions. So some of the motivation of our research is in the end, can we still leverage quantum coherence, but in nanoscale devices which can operate at ambient conditions? And of course, I'm not alone to work in these directions, and there are a lot of groups studying different systems which could alleviate the need for this big machine. The ambition is not to do quantum computers probably based on that. We will still have different applications. And one of them is quantum transduction. So quantum transduction is a very general term, meaning the coherent transfer of information. I mean, classical transduction itself means the coherent transfer of information from one domain to another. So it can be between two electromagnetic waves or between a force field and an optical field. And quantum transduction is just the extension of this process, which preserves quantum coherence, quantum states, quantum statistics. And for that purpose, mechanical oscillators or mechanical vibrations in general have emerged as a very versatile platform. So they can be coupled on the one hand to optical fields, and on the other hand to something else. So it can be another optical field at different frequency, as I will show in the second part, or it can be a qubit. It can be some microwave cavities. So this is really a large effort. Now you have some reviews here. So let's first look. So I claim that these two coupling can be coherent. So I will first describe this, this first coupling here, which is usually what we call the optomechanical coupling. So you have on one hand an optical field which is oscillating, at very high frequency, hundreds of terahertz. And you have here a mechanical element which has an oscillation frequency omega, which is usually much smaller. So in most systems studied so far, it's gigahertz, megahertz. And I will show that we can extend this to terahertz using molecular vibrations. So what is this interaction? So this interaction can be very simply understood if you consider monochromatic wave, which is bouncing on this mirror, and this mirror itself is moving. So you will change the path. So it will create a phase shift on the reflected light. And you can do the calculation, you can find this expression, and if you expand this term to first order, you will find still the carrier wave frequency plus two side lengths. Actually, this is already expanded here. So what you find is more complex, and if you do the expansion, you find the carrier plus this term to first order, which you see it's quite interesting because it's shifted in frequency. So if you have a spectrum analyzer, you can see this sideband. Even if they are much smaller than the energy in the main beam, and they bear information on the displacement. And this is why there's this process being used in gravitational wave detectors in particular. So you can measure very small displacement using that. So eventually people started to worry in the 70s when they were designing these big gravitational wave observatories. A few researchers were wondering what will be the limit of the sensitivity of this. Here, it seems like we can detect arbitrary small delta X if we have a good enough detector and enough laser power. But in the end, they realized that something will limit the detection sensitivity, and this is where a quantum description is needed. So when you quantize the electromagnetic field that is bouncing on this mirror, on this oscillator, and you also quantize the oscillator itself, you realize that what is happening in this interaction is that some photons are getting energy from the creation or annihilation of vibrations, phonons, which they are called. So that's interesting, and it leads to, so I won't have time to explain this in detail, but this process leads to a so-called quantum back actions, which in this picture, you can think of each time the photon is bouncing, it can impart momentum to the mirror, but in a random way, because this is irreducible shot noise of the laser beam. So the consequence for gravitational wave detection, which was pointed out by Kate, considering this controversy whether quantum mechanical effect can disturb measurement, and yes, they do. That's a conclusion, which reach. So here the plot shows that as you increase the laser power and you want to measure the displacement, you first gain because you reduce shot noise relative to your signal. This is the usual 1/square root of n gain. So this slope is half 1/2 on the log scale, and then you start to have the effect of quantum back action. So it seems that quantum back action is a nuisance. In fact, it's very interesting to probe quantum back action because you see that during this process, you expect some entanglement of some form between the photons that are gaining or losing energy and between these vibrations, because definitely they get correlated during this process because they exchange single quanta of energy. So one of the motivations in the first part I will show you is to study this process of quantum back action by using single photon detection on the scattered beam at this sideband frequency. So most of the photons will get scattered without changing their energy. But if we post-select the photons that are scattered after having lost or gained energy, we can start to evidence these quantum correlations. Yes. So the idea is simple. Now, the problem is that you have this nice quantum mixture, but on top of that, you have thermal noise. So your mechanical oscillator is coupled to a thermal bath, whatever you do. And if you consider the systems that have been studied so far, even the smallest one, like I was studying with Tobias Kippenberg, which are nanofabricated silicon beams, they oscillate at GHz frequency. So suppressing thermal noise requires to go to 30 millikelvin, which can be achieved in dilution fridge or by sideband cooling, but it's adding some complexity. So my goal was very simple, was to say, okay, let's look at natural oscillators, which are internal vibrations in molecules or in solids, which naturally oscillates at tens of terahertz and are at room temperature in the ground state, so we can start to see this quantum correlation and this quantum effects. And this is what I will discuss briefly now. So first, I'll be very short. I'll show you a few experiments we did to study this quantum back action can be used to evidence quantum correlations between light and vibrations at room temperature. And there we had to use ultra-fast laser pulses to monitor these correlations, because we are working now with systems, these molecular vibrations, they decay very fast, they decohere very fast. So we have to adapt a bit the techniques that we are using, which are different from what is traditionally used in cavity optomechanics. And then I will show you what I discussed before, an example of optomechanical transduction using molecular vibrations, which in this case, the measurements are classical. We have not yet done anything that proves quantum coherence, but we have good reasons to believe this is quantum coherent. We still have to prove it by notably increasing the efficiency of the process. Okay, so just to come back to the picture I showed before, if you now deal with molecular vibrations, this picture of light bouncing on the mirror, it's not so accurate, but nevertheless, you find the same results. So we have to use this simplified picture is just to show you how we get the to understand Raman scattering with molecular elements. So if you shine light again, oscillating at omega naught, on some molecules, each vibrational mode can be considered as a first approximation as a harmonic oscillator, and the displacement of this harmonicus or of this vibrational band will affect the induced dipole. And this induced dipole will therefore, so this is embodied in this Raman tensor. So I will go quickly here. Bottom line is the incoming field also gets modulated, this time in intensity, and this creates also these two sidebands, which by the way we call the stocks on the lower energy and anti-stocks on the higher energy. Now this picture doesn't explain properly, for example, the relative intensity of these two sidebands. So we have to, for that, to take into account the quantum nature of the molecule itself, or anything that is vibrating. And in this case, we find this very simple picture where the Stokes process corresponds to the excitation of a pair of a photon, which is at a different frequency from the pump, and a phonon. So in all the experiments I will show you then, this pump is approximated by a classical beam. So this is so-called parametric approximation. So in the end, in the Hamiltonian, I don't show here, we have a term where there is some coupling strength and then a term which creates these pairs, like in a squeezing experiment with a nonlinear crystal, except that here one field is a phonon. And the other process will, it's so-called beam speeder interaction or some swapping Hamiltonian, which can collect or transfer the energy from the phonon into an anti-Stokes photon. And that's the two processes we use. And we developed this, this technique of pump probe experiments to probe these two processes. And here I remind you that what I called quantum back action before, in particular in Raman scattering, it's really related to the Stokes process. So the idea is that if you want to measure the vibrational mode of a molecule, you have to shine light on it. So you have to scatter photons. And these photons will create phonons or vibrations, but at random, because in the end, you don't control this process and it's stimulated by vacuum fluctuations. So you induce in the end some noise on your molecule, or you slightly increase the effective temperature of this phonon mode, which is related to also what people call vibrational pumping in the earlier days of observers. So this is more for people who know about this world. Okay, so now the issue with the molecules compared to other bigger mechanical oscillators is that they have extremely small Raman cross sections. So it's impossible to study a single molecule in vacuum using these processes. And as I said before, they are losing their coherence and their energy very fast on picosecond time scale, at least if they are in the solid state. So that's the systems we study. So in this first part, what we did is to circumvent this very small cross section. We are using bulk systems. So we are using billions and billions or tens of billions of individual units. So either we use crystals, so where if you want, the molecule is a carbon-carbon bond, which is repeated quasi infinitely, or we use true molecules like carbon disulfide, which is like CO2 in a liquid, and there we also probe billions of molecules. So we are really working with collective modes, and nevertheless, I'll show you that this collective mode, they can behave if you do if your experiment has a proper geometry, they can behave as a single entity, as a single harmonic oscillator or quasi-harmonic oscillator. So very briefly, because I don't have time to review everything, so we first developed this pump probe technique with, let's say, using two very short pulses, like 100, 200 femtoseconds at two different colors, and some filtering and single photon detection, so that we can really look at this process of creating a vibration and annihilating a vibration as a function of the delay between these two pulses. And with that, one of the main first results was to show that indeed these correlations that are created in Raman scattering, without further engineering, I mean, it's really just a spontaneous interaction, they can be leveraged to show Bell correlations between photon and phonons, or between light and vibrations. And Bell correlations are the strongest form of entanglement you can have in a bipartite system. So they are very, very strong, if you want. And what I will just describe now is something more recent we did. So here we were working with diamond. So in diamond, there is always a question of, can we think of this as as a set of molecular oscillator, or should we really directly talk about the phonon dispersion, and therefore these are already collective modes? So to clarify this point, we studied the liquid. So there in the liquid, clearly the molecules are independent, they live their own life. And in the liquid, actually the question we asked, so this is the experiment, we shine 2 pulses, which can be spaced by picoseconds, you will see. Very importantly, you will see after filtering, we collect the light in a single mode fiber. And we look at this simple experiment. So we create a Stokes photon and then look at the correlation between these 2 detectors. And the question we wanted to ask is, so our experiment only keeps the event where there was a Stokes photon emitted in the first place. So sometimes nothing happens and then the light is just going through. But if there is a Stokes photon, so we know that we created 1 unit of vibration. We could call it a phonon, even though it's maybe not appropriate for this liquid, but we created 1 quantum of vibrational energy. The question is, should we describe it as 1 molecule that has been randomly excited within these billions of molecules, which is what you will find if you look at textbook on Raman scattering. If you look at standard textbooks, they say, okay, if you do spontaneous Raman scattering, so here we are in a regime where there is much less than 1 probability to emit, so it's more like 1% or 0.1% probability to emit a Stokes photon, so there is no stimulated process. So most textbooks, they would say, okay, this is an incoherent process, and then by extension, you might say the final state is some mixed state with 1 molecule excited at random. So well, here actually it's not, you have to understand that this is 1 molecule excited at random and the other ones are not excited. But if you are more from quantum optics, in particular if you are familiar, sorry we don't see here, with this DLCZ proposal, which uses as a fundamental unit, the idea that in this case you should, even if you have an ensemble of 2-level system or oscillators, you should be ending up with a coherent superposition, because if the geometry of the experiment does not allow to obtain information on which molecule was excited, then you have to consider that this is a coherent superposition of 1 excitation shared by all the molecules. So we wanted to address this question, and it turns out in CS2, the liquid itself is made of, first there are different isotopes, and there are also molecules in different excited states due to thermal excitation. And because of an harmonicity in the molecular vibration, depending on their thermal excitation, they will have slightly different vibrational shifts. So you have a distribution of vibrational energies, and this is what we will use. So we will use this fact by, so the idea is that when we shine the very short pulses here to excite the Stokes photon, the bandwidth of the pulse in the frequency domain is much bigger than this tiny splitting. So the information on which vibrational subset was excited is erased by the design of the laser pulse. So this allows us to then, so if now we excite 1 molecule at random, it will belong to 1 of these subsets. And if we repeat the experiment, we will see an incoherent sum of different dynamics related to these different subsets. But if indeed we create this superposition, because we have different frequency, we expect some beating. We expect some beats, not due to this, like in sound waves or anything. And indeed, that's what we see. So this is a measurement, and we see very clearly. I mean, the first one is very clear; the other one are a bit washed by noise, unfortunately. But still, we very clearly see that. So these curves are not really fixed; they are really very much constrained by the spectrum I showed you before. So we have to respect this intensity and frequency. And you see that if we plug this in, we can recover the oscillations due to this quantum beats between the different subsets. And if we assume that this mixture is excited, we clearly fail. Okay, so that I think is, at least we believe, it's one of the first very clear evidence that even though you are in the liquid at room temperature and so on, using spontaneous Raman scattering, you can still recover really the same physics as in rare earth crystal or things that are used for quantum memory, for example, albeit now, of course, on much shorter time scale. But the detection geometry is very important. So if you don't use this single mode fiber in detection, you now have many spatial modes contributing to the signal, and this really kills this oscillation very quickly. But we don't have a full theory for that, unfortunately. I mean, for this very simple tone model, it works, but taking into account all the spatial modes is not something we are able to do so. Yeah, good. So I don't know actually if you have questions on this part, if you want to ask now, if you prefer to wait until the end, or if there is anything you got completely lost about, maybe it's best to ask before I go too far. Yeah.
So here you use a polar solvent, I imagine, because it's like the solute is.
It's pure CS2.
Yeah,
there is no solvent.
Okay.
CS2 is a liquid.
Do you have any insight if what would happen if you add some polar solvent to your ensemble or some polar interaction or something, let's say, which would create some coordination geometry around your solute? Saying, would you think that it might be enhanced, this effect, or suppressed?
Yeah, it can be very complex. Some sort of short range order or something like that. Yeah, and I think these questions have been studied or are being studied by other means, such as second harmonic generation or some frequency generation, because at least I know that at EPFL there is Sylvie Rock who is doing this on water, and she has been studying, this of much order there is in water. All this is affecting this Raman process. Honestly, I don't know. I've not thought about it. So here also for example, these time scales, I'm not expert enough in molecular dynamics to tell you if it's related to the rotational motion of the molecule or if it's some sort of internal decoherence. It's rather complex, actually. I've not yet looked so much into the details. Yeah, that's a good question.
So,
yeah.
Here also this theory curve that you got, that is not just a fit. Is that like a Fourier transform of the spectrum, or
some sort of it? Yeah. Yeah. I mean, it's basically we really make the sum of complex numbers which oscillate at this different frequency and take the modulus square. So it's the interference pattern related to this. So the three parameters are the relative phases, which we don't know what is setting them in a sense. Something intrinsic that comes out, which seems to be fixed because of course, we have to acquire a lot of photons. So it seems that this relative phases is fixed by something, by the Raman activity, by the geometry, we don't know. But the phases we have to fix. The relative phases, so but there is only really one that is really important. So one or two relative phases which are important. And then there is also a scaling because, of course, depending on the noise we have, this G2 might be bigger or smaller, but that's something we have to do. But that's it. So the rest, the intensity of the different, or the amplitude of the different components and their relative frequencies are fixed by the continuous wave Raman spectrum. So we are pretty confident that what we are seeing is related. That's the best evidence we have. Good. So then, in the second part, I'll discuss this other work, which is also more related to what we are collaborating on with, or we were collaborating on in the recent past with Diego, which is the idea of using these molecular vibrations in some sort of transduction process, and more specifically, we will demonstrate conversion between infra or mid-infrared field and optical field. So the idea is the following: we will transfer information from the mid-infrared, which is resonant with this molecular vibration. So here we use a molecule that is oscillating at one of the molecular mode of this biphenyl molecule as a resonance at 32.4 terahertz. So we will have a coherent resonance interaction here, and here we will use this Raman interaction and try to see if we can convert coherently from here to there. And as you see, it could also work the other way, still to be demonstrated. Yes, so system we designed for that, and I quickly skip over different steps, and this is really not a unique possibility, but we had to find a way to boost these two interactions. Because what I showed you before was to use bulk things. So if you want to do this process in a bulk material, you will face a few issues. The first one is it transparent at both frequencies? Probably not, because if it has a resonance here, it will absorb mid-infrared. And second, even if it were, can you achieve phase matching? Because this effect is very weak in the bulk, so you have to use long distance. And phase matching between mid-infrared and visible, it's a lot of, it's more than a decade of difference in frequency. It's really tough. There has been very few work on that. And it's very narrow band, it requires a specific geometry. So we wanted to avoid these things by working in very small nano cavities where definitely this thing is sub-wavelength. So this dimension is 150 nanometer. So this slit here, as I will show you the simulation, is acting as an infrared antenna for 32 terahertz. And this nanoparticle is coupled to the visible field, and both fields get amplified in these gaps. And the way this sample is made is this is all gold. Actually, I can show you the picture on the right. It's all gold. Then we functionalize the gold surface with, so etch these grooves. We functionalize with molecules. So there is a single layer of this BPT molecule. And finally, we drop cast some nanoparticles in a more or less controlled way. So some samples, we have a lot of them. Some of them we struggle. But in the end, when it works, we get good devices. So this is what I was mentioning. So if you simulate this structure and you look at the cross-section here, you see that for normal incidence, you have a big field enhancement for the mid-infrared. So we have enhancement actually on the order of 550 for the field. So it's really close to the quantum or to the limit before we start with tunneling and other things. And for the visible, we also get very decent values. But as you can see already, we are not very good at the overlaps. So the mid-IR field is not as confined as the visible field. And this is one of the main still limitation of this geometry, is that we think the field overlap is not great. So the molecules that get excited by the mid-infrared light are not all the same as the one excited by the Raman process, which reduces the efficiency. So that we really have to work on it. Nevertheless, if you now consider the molecules in the hotspot, and you were to compare the efficiency of this transduction process to the far field, or to the free space. So you take the same molecule, you put one in here and another one in free space, and you look at the efficiency. We estimate and confirm experimentally that the boost in efficiency is 13 orders of magnitude. So this is really large, because it's you see it's a nonlinear effect which involves the intensity of the mid-IR field and the fourth power of the electric field for the Raman scattering. So we have the sixth power of the field in the end. So let's see if it works. So this is a measurement of continuous wave Raman scattering from such a nano cavity. So you see very clearly in the Stokes sideband at lower frequency than the laser, all the bands coming to different vibrational modes of the molecules. The anti-Stokes, as you expect from at this large Raman shift at room temperature, is very weak because there is very little thermal population in the vibrational modes. So the setup actually is described here on the right. So this is just very schematic, but it's a confocal Raman scattering. Now we will first, before I show you what happens with the mid-IR, it's very interesting to look with a high resolution spectrometer, something that usually people don't do in Raman spectroscopy. They are not so much interested in the line width of the slit. But if you look with a much bigger spectrometer, you'll find that first you can look at the line width, which is related to the coherence time of the vibrations. And you can also nicely see this asymmetry as well due to the low thermal population. So I'll show you it's important to look very close to completely understand the process. Now, we shine on the mid-infrared light. So we shine it from below through another objective. So it goes through the silicon substrate. And now you get the green spectrum. So if I go back to the other one, you see that in the dashed area, here in particular on the anti-Stokes, you had pretty much nothing from the Raman alone. And now if you shine mid-IR light, you get a complete boost in the anti-stocks, but also a change in the stocks. So from that picture, it might seem what you are doing is just some sort of, if not population inversion, but maybe just some, you are populating a specific vibrational mode, and therefore the stocks and anti-stocks becomes almost equal. But this picture is actually not really correct, and this is where you have to look. So the sidebands are where they should be, so they are plus minus the frequency of the mid-infrared light. But now if you look, so the resolution is maybe not great, but I hope you can see it that on top of this gray area, which was the spontaneous Raman signal, you get this orange peak, which is now due to the mid-infrared mixing with mid-infrared. So I'll show you here a bit better. So actually, you're not changing so much the thermal state of the molecule, you are adding a coherent component onto it. And if you tune the mid-infrared laser and bring it to shorter or smaller frequency, this peak will shift toward your laser, as it should be. So we don't have a large tuning range, but enough to evidence two things. One is that the line width of this upconversion is really narrow, limited by your spectrometer, and we believe it's in the end limited by the lasers, which would be compatible with a coherent process. I put here a picture which I think describes what's happening. You have a thermal state, which is this gray area, and then it's coherently displaced by the mid-IR field, which gives rise to the spectrum with a spike. And the other thing you can see here that the efficiency of the process does follow the spontaneous line shape of the Raman signal. So in a sense, the bandwidth of the process is limited by the mechanical bandwidth, which is coherent, which is consistent with the idea of optomechanical transduction. Okay. Yeah, so what can we do with that? So I'll come back a bit to the efficiency and so on, but one of the motivations that we hope we could do as really a concrete application would be to use this upconversion for mid-IR spectroscopy in general. So you know that if now you want to study materials, molecules, whatever, almost all the time you will at some point want to do infrared absorption. And for that, because it's sensitive specifically to this vibration mode, so for that you need to go and find a Fourier transform infrared spectrometer, which remains a bulky and expensive device. On the other hand, in the visible, you have things like in your cell phone, we have some cameras which are pretty good, and you can buy this tiny spectrometer from Ocean Optics, which are actually even better than what you can do with an FTIR and much less expensive and much more compact. So the general idea is that if you can make a device which can convert the spectrum from the mid-infrared to the visible, you could then use it as an add-on to such a spectrometer to extend it to the infrared, speaking. But for that, it has to be relatively efficient. And at the moment, it's not the case. So first, bear in mind, we really study a single nanocavity. So we are really looking at this process, which is generated by, we estimate between 100 and 1,000 molecules. So it's really, we're really looking at small things. And what we estimate is that from the mid-IR to, so again, because of this overlap problem, we have to be careful. So we think that 10 to the minus 5 is the probability that an incoming mid-infrared photon is exciting molecules which are themselves coupled to Raman scattering. So we don't know the absolute absorption of mid-IR. It's probably on the order of 1%, maybe something like that. But most of it is absorbed inside either the metal or some molecules which are not coupled to the Raman. And then we can know that for this incoming pump power, the efficiency of Raman scattering is 10 to the minus 5. So that's a probability that vibration gets converted into an anti-Stokes or Stokes photon. And finally, we have another inefficiency, which is due to the fact that some of this light is going into surface plasmons, into other modes which are not collected. So overall, yes, the efficiency is not great. Nevertheless, because the process is coherent, if you are careful and look at the signal using this high-resolution spectrometer, you can detect signal which are on the order of 10 nanowatt per square micron in terms of power density in the mid-IR. So it's already not that bad, but it's not competitive in terms of detector with other technologies today. But it's coherent, so that's what is not possible with other techniques. And yeah, as we studied with Diego and with Philippe before, we know from theory that if we optimize, so here we consider a different design of double antenna, and we found that in some optimal regime of pump power, also using pulsed excitation, we were expecting to be able to detect single mid-IR photons. So there is still a lot of room between these two things, yeah, to be covered. And to be a bit more quantitative for the audience here, these are some numbers. So again, I think there are a lot of work to be done in terms of simulations or I don't know, theory to understand how we go from here to here and from here to here. That's usually not something theorists worry about so much. So usually the theory considers some intracavity photon number and some sort of coupling rate, but experimentally, we focus the light, we don't have a plane wave, it's very hard still to date, even in COMSOL, we have not yet been able to even simulate a strongly focused excitation of these cavities, despite some efforts with people who are good at COMSOL, so it's not a trivial task. So yeah, there is a lot of uncertainty in how to translate the power we send on the sample to how much plasmons or what is the occupancy of the near field. So I think that's a challenge we have to solve. Then yeah, there is some uncertainty into the number of molecules, the exact geometry for sure. But within the uncertainties, if you consider the simulation I've showed here, to give you some numbers, so the dissipation rate, this we know pretty well. That's relatively, I would say within a factor of 2, we are pretty confident. Vacuum coupling, we estimate, using mode volume, which itself is related to the Purcell effect. So we can estimate these two numbers for the vacuum coupling rate, which would scale with the square root of the number of molecules. So they are quite similar actually in tens of gigahertz. And the cooperativity, which I think is in the end the most important parameter, which defines the efficiency of this process. So in the mid-infrared, we can reach with this design cooperativity when multiplied by the number of molecules could be on the order of maybe 10 to the minus 2. And in the visible, we have to multiply by the number of molecules and the number of pump photons. So this is this parametric amplification. But even then, again, I don't think this number is larger than 1. It's probably a fraction of maybe 0.1, 0.01, we don't know exactly. The number of molecules is what it is here. So we are still way below 1. So that's, I think here what I want to show is that contrary to other optomechanical systems, where cooperativity of 1 is kind of routine, or at least it's achieved relatively easily, in molecular optomechanics, we are still relatively far from it, only using ultra-fast excitation. So we have not yet combined ultra-fast excitation and plasmonics. So Jeremy Bamberg has done it and is seeing some stuff, but the problem is that a lot of other things can happen if you start very short pulses on a plasmonic cavity. So we have to figure this out before training some stuff. But yeah, the best would be to optimize this cavity further, and there is room for it, so that even under continuous wave excitation, we could reach this, get these two cooperativity close to 1, and then we would be in business. Yeah. Yeah, and there are things we can do. So really optimizing the number of molecules contributing, leveraging this collective enhancement, and improving the field overlap, solving this issue I told you before about coupling to the far field. And also here we have a simple way to boost here this number by having cavities which are more resilient to pump power. At the moment, if we send 100 microwatt, we start to see instability in the cavity. Yes, and the molecules themselves can be engineered as well. So for that, we have been working with chemists in UCL, in London, and there are Edina Rosta and Susie. They have been developing some method using DFT and machine learning to explore very large number of molecules and get some rough idea of their, relatively precise idea of their Raman and IR activity, from which we can also compute the some frequency or frequency conversions cross section. So the molecules we have been using so far in this plot is somewhere here. So you see here is Raman activity, and here is some frequency. So in principle, by choosing better molecules, we could already boost by a factor of 1,000 the conversion efficiency. Now, in practice, the problem is, and we are exploring these things at the moment, but the problem is, are these molecules forming these nice monolayers? That's really the tricky point. They look very good, but to get there in this nanometer gap, you need to have a good interaction with gold and other things. So that's what we are studying at the moment. But overall, I would say to conclude that in terms of optomechanical transduction or frequency conversion, we still have a lot of work to optimize the conversion efficiency. That's already a rich problem. There are also questions about the coherence of the process. Right now, we say it's, at least it seems classically coherent from the line width of the peak, but can we measure photon statistics? Can we show that it's coherent and not thermal and this kind of thing? So that's something we can do in the future. Collective effects, from theory, we should have this quadratic scaling in the end of the conversion efficiency with number of molecules. It's not being demonstrated experimentally, so that would be an interesting thing to do. The question of reverse operation, I find interesting, especially if we can have a large mid-infrared coupling, maybe reach into the vibrational strong coupling regime. Can we use this as a mid-IR or terahertz emitter in the reverse way? And there are more questions also. Can we see a conversion from single molecules where things can become anharmonic and, let's say, non-linear in the sense that it's not a product of two linear processes? That's a few things to be done. Applications, I guess, for many others. And more generally, for molecular optomechanics as a field, which is quite new, at least in its name, I think at this stage we are in this regime where the theory is already much better than the first one we proposed with Philippe and Tobias Kippenberg 7 years ago or so, but it's still quite far from the experimental systems, which themselves needs to be also simplified and more controlled. So in experiments, the field of surface enhanced Raman scattering, was not so much bothered on having some well-controlled system with a non-mod volume and things like that. So this is really the novelty with molecular optomechanics from an experimental point of view, is that the effort is really on controlling the system parameters and making it closer to the model. But of course, there is a mutual effort to do so that the model is also taking into account there some of the complexities of the systems. And these are some of the challenges which remain. So first, this was the original proposal that we had with Philippe. Is something I didn't talk about today, is that in this optomechanical cavities, you have a new phenomenon which is also not captured by the simple Raman scattering picture. It's called dynamical back action. So it's really like phonon lasing. Okay, so it's the idea that at some point you generate phonon faster than they decohere. So you have like in an OPO, you start to lace in one of these down-converted fields. So that remains to be proven if it's reachable or not. On paper, it could be, it's still a bit unclear. But that would be, what would be interesting is that it would be really a new enhancement mechanism, something that is not captured by the conventional field enhancement picture of cells. So that could boost your signal even further. So that was the original idea. And there have been other recent proposals. For example, what is the role of dissipative coupling? So here, I've only talked about so-called dispersive coupling, where actually you have let's say the vibration of the molecule is changing the polarizability of the molecule, and therefore, if you put it in the cavity, it's shifting the frequency of the cavity. But actually, if the cavity is shifting, it can also change dissipation rates in the system. It's so-called dissipative coupling in optomechanics. And there was a paper recently, I didn't have time to add the citation, so I'm sorry for that, but a group recently studied this and claimed that it could really be in favor of stronger cooperativity, also still to be demonstrated. And yeah, there are other topics such as developing new cavities with higher Q factor, retaining small mode volume. For example, Ewald Verhagen has been pioneering this idea, and theoretically, of course, there has been more work on hybrid cavities, which are aims to solve these issues. And molecular engineering is another direction. So there are a lot of things. It's quite rich. Yes, this I will skip. And I wanted to conclude also with showing a bit of the other things we might want to discuss here. So I have one small project. I mean, small. It's only one PhD student, but it's very complex. So it's challenging. So we want to combine this plasmonic measure, this Raman measurement and optical excitation with transport. So we have to isolate single nanocavity, but now have them connected to electron, to a battery, and then see what happens when electrons go through the molecule, might couple also to photons. So it's quite challenging and might lead some results in some years. And another project with Guillermo Acuna is to control the number of molecules we have inside through DNA origami. So now we use other structures such as dimers, which are then placed on mirror. And then, yeah, these are some processes where we start to see. So here we have fluorophores. So contrary to everything I showed before, which was really far from any electronic transition, so it was off resonant Raman scattering. Here we are exciting electronic state in the molecule, but you see in this plot that the purple lines, which are the bare dyes at low temperature at 4 Kelvin, this emission gets completely reshaped by the plasmon, which are the blue lines when it's coupled to the plasmon, in a way that seems to be beyond just the Purcell effect. So there seems to be additional dephasing or some phonon-assisted process we don't know at the moment. So that you can feed emission even up to 300 milli from the zero phonon line. Yeah, and another part of my team which is growing at the moment, is working on, actually the title is not probably exhaustive. So we do both some sensing with ND centers, for those who know ND centers, nitrogen vacancy centers. But we also have a new project where we do more generally diamond photonics, also for Raman scattering, which is just starting at the moment. So we work with diamond as a platform for photonics and for sensing. Yes, so with that, I'd like to conclude by thanking my team. So here at the moment, I have 6 PhD students and 3 for postdocs, and funding, yes, by ERC and FNS, and that's it. Thank you for listening, and of course, I'm happy if you have questions.
Thank you very much, Christophe. Let's start with the questions. Petros?
Yeah. So I have one question. Do you have any insight where you have this sharp 1 gigahertz peak? Why is it 1 gigahertz? It's not,
Yes.
let's say, comparable to any other characteristic frequency of the system?
Yeah, so I can answer that. So 1 gigahertz is actually here in the picture, it was 7 gigahertz or so, because it's a resolution of our spectrometer. That's it. So
practically even sharper?
So
and you don't?
Yeah, my guess is that it's as sharp as the lasers, which themselves are around 1 megahertz.
Okay.
So I think it's 1 megahertz, not 1 gigahertz. But at the moment we can measure by the resolution of our stuff. So we went from 10 to 1 gigahertz by doing scanning étalon spectroscopy. But yeah, going beyond that is difficult. So that's where we should do some sort of, let's say, long arm interferometry, like some sort of measuring G1 in a time domain. It's not something we have done yet.
And another question. So you have an optical cavity, you have this optical mode, the plasmonic one, which has a line width of 23 terahertz, right? Or not?
So you mean
like my point would be that the detuning is symmetric and equal sideband generation, the Raman one, lies outside the cavity.
Yes. Sorry, right. I removed that. So actually, it's no, that's a very good point. So in fact, I had this in other slides.
It was in the last one where you have.
But probably what you mean is that. So let's say if my laser is resonant with this mode, then the stocks and anti-stocks will be not resonant. Or is it your question?
Exactly. Yeah. Like you don't support the structure. Yeah. You don't support a second cavity mode.
So it does
that you could like let's say broadcast the signal of the stocks or the anti-stocks mode.
No. So I'm sorry, I removed this plot. So if you're interested, I can show you later. But actually, if you look at the local density of states or photonic states as a function of frequency here, it has at least 2 modes and even more. So actually, one of the authors, Wakian, who with doing all this simulation, we are preparing with him a bit longer paper where we explore really this structure in terms of electromagnetic mode and so on. So it does have multiple modes in the visible, especially if you consider the facets of this nanoparticle. It's a bit like the nanoparticle on mirrors. It's not just like a sphere where you would have just a dipole mode. It has actually many modes inside. But this is making things even harder to compute mode overlaps. But clearly, it is enhanced over a really broad bandwidth in the visible. So both the stocks and anti-stocks are boosted by this plasmonic effect, actually.
Boosted, but still, you don't have a second, let's say, cavity mode in the anti-stocks frequency. Because if you had it, then it would really enhance the signal by means of.
No, but we do have it close to the anti-stocks. So I think it's hard to tell exactly where are the modes, but I think we really boost quite a lot the anti-stocks as well. Yeah. Well, it's hard to be extremely quantitative, but we do have this effect. Maybe not optimal, but we do have it.
So just to put that, to try and put that answer into language that I've used before, basically your antenna is resonant both at your input frequency and at both your output frequencies.
Yes, to some extent, maybe not at like maximum resonant at all frequency, but this field enhancement of about 100 something is quite broad.
Yeah.
It's quite broadband.
And to follow up on this, it seems like you guys are doing a ton of work. You're writing another paper on the antenna stuff, so maybe this is a little redundant, but I'm curious to see whether or not working with a material that has slightly lower Druva damping rate would be useful. So like switching to like silver rather than gold. I realize there's experimental difficulties with that, but it's my understanding that these antennas generally have field enhancements that go like one on gamma, where gamma is the Druva damping rate. And then my other question was, if it really is the field enhancement in these gaps that you're obsessed with, which makes sense, why not use particles that are just they're little, for lack of a better word, sharper, right? Like with sharp points that tend to generate sort of like very large but kind of unreliable field enhancement.
Yeah. Okay. So yeah, very good question. So using silver for sure would boost further the field and make sharper resonances. So that would be definitely most likely beneficial, except indeed for oxidation. So that's but we have worked with silver in the past. We see also much more of blinking. So I've not discussed here, but that's something that we see always in not so much in these cavities, fortunately, but in most geometry for Raman scattering, you see a lot of. Now it's been called picocavity, and it has been taking new names, but it's basically Raman blinking, if you want. So there's a lot of fluctuation in the signal. So this happens also more with silver, actually. It's much more reactive silver, and it creates more of this background, and it's a bit tricky. Now, using sharp points is also something we are trying now, specifically to generate this picocavity, because we'd like to see how they behave in a conversion. But for the signal itself, this is where things get a bit more interesting. So in the end, what you are worried about is this total efficiency, where you have the square root of the number of molecules entering in each coupling rate. And if you make the thing sharper, maybe you will get more field enhancement, but you will get less molecules. And altogether, I don't think it's beneficial to the process. So whether it is beneficial or not will depend on how much manpower you can put and different small details like that. But overall, I can say I'm quite confident that if you are really worried about efficiency, what you should work here is not so much the field enhancement at the moment, is rather the mode overlap and coupling to far field, rather than the field enhancement itself. It depends. If you're interested in single molecule signal, what you say is true. Then you want to have the highest possible signal. But if you are interested in the collective effect, it's not the same. So
okay, so like in general, a general rule of thumb here would be if you need lots of molecules to get any signal out, You're better off optimizing a sort of flat gap using material tweaks than if you are to try and optimize the geometry. So.
Yeah. So you can write down actually the scaling law. It scales with number of molecules, with mode volumes, and then depending on the assumption. So if you assume that the molecules fill the entire mode volume, and that your pump power is not a limiting factor, so because if you increase the mode volume, you also need to increase the number of plasmons you excite.
Right.
And in the end, if you do that, then the scaling is, let's say, independent of mode volume at some point. But in reality, usually the pump power cannot be as high as you want. Yeah, we can discuss at length a bit with that. It's an interesting formal problem to see on paper what is optimal, but yeah, there are some assumptions.
Yeah, it's not. Yeah. In the end, it's complicated in itself.
Yeah. Okay. There any other question, Johannes?
So really nice talk. If I want to use this as a detector in the infrared, I guess the limitation I have is that I can only detect frequencies where I have a Raman transition.
Yeah.
So it's
yeah. So that was the motivation. That's for sure a limitation. Although, well, yes and no. We don't know yet. So that was the motivation for this tool. Is that then you can find molecules with a lot of bands. You can combine them so to cover a broader range. And I say yes and no because at the moment we are trying to put some other molecules inside, and it seems that we don't know at the moment of the efficient and what is the reality, but it could be that there is also an off-resonant contribution to this conversion process, which is not due to the vibration, but some general electronic nonlinearity in the molecule, which is expected. If you have any molecule which has some sort of Chi2 effect, it could be boosted by this cavity the same way as this optomechanical effect. So I think there is also room to explore molecules which are maybe more used in nonlinear optics, which are large Chi2, and put them inside. And in this way, it would be very broadband, or maybe 2D materials as well. So yeah, that's still also to be explored as well. But in itself, that's a limitation.
Yeah, so related to this part, right? So you're using an online or this database, but I imagine that these signatures are from the isolated molecules.
Yeah.
So how much do you expect that these kind of things, like some frequency generation, can change the moment that you place it on the surface, become some sort of one layer?
Yeah, no, very good point. So what we do is well, this is what they do in London, because I don't do DFT, but they put a sulfur gold bond. So it already captures part of the effect that you have by using gold. But there has been work, I don't know if it's published, but in the European project, we work also with Javier Astura and people in San Sebastian. And I know they have been studying what happens when you put bigger and bigger gold clusters. So there is all part of the work in DFT to simulate more realistic systems, including more of the gold, maybe also several molecules. And for sure, if you just the connection to the gold can alter the Raman cross-section, but usually it's favorable. So I think it's related to what people call the chemical enhancement in surface, although I've never really understood what is the frontier between these two things, but it usually helps. As far as I understand from the theory, you get a bit more enhancement because of that. But all it really affects in details. In this model, at least, we just consider one gold atom, and it already helped to change a bit the vibrational modes and make it a bit more realistic.
No, I have a question myself. Okay.
Because there was two on the chat also.
Yeah, I'm waiting for them to pass me the question. So I have a question. It's not so relevant to this up conversion process, but I was wondering, this is something that is always at the back of my mind. And you mentioned the problems that come with metals and plasmonics and so on. Do you have any experience with metallluminescence? And if you are thinking of down conversion, and so is this something because in your cavities where you want resonances that are far apart, do you see luminescence that, or have you looked at the various structures you have down conversion?
Down conversion from what to what?
Just out of the metal. This is something I discussed with Guillermo several times.
So if you look at this paper here, also by well in Japan, we studied the luminescence from gold. itself. So yes, there is luminescence, especially if you excite at 532 for gold, because then you have some interband transition. So there can be relatively strong, and what we studied in its favor is that it can fluctuate a lot and have line width which is much sharper than the plasmon line width. So this luminescence is not only, at least when we excite at 532, we are sure it's not only just a broad electronic background. It can, from what data we speculate, it can really come from some sort of confined state in the gold. But really, honestly, we don't have a good theory for that. But we see that you can have pretty sharp peaks emerging from the broad plasmonic background. So overall, on average, if you average for 1 minute, you see some luminescence which resembles the plasmon emission. But if you go fast, you see actually some sharp emission popping out randomly. So this is one of the effects we see related to luminescence. And if you go to silver, this can be really crazy. Yeah. And at low temperature, it can be extremely sharp. So we haven't yet explored these things because they are a bit random and so on, but they are there. They are more nuisance for most of the things we do, but maybe they could be useful in some way.
I was more worried if this is a problem.
Yeah, it can be a problem, but fortunately, if you excite at 700 nanometer like that, you really don't have much electronic transition in gold. So you have some still like electronic Raman, things like that, but they are relatively weak and not so problematic.
Okay, so we have a question in the audience. So I don't know, Walter?
Hello, can you hear me?
Yeah.
Okay. If you want to make sort of a phonon maser, you need sufficient mean free path for the phonons. But if you work at room temperature, and that's only a few atomic distances, then it gets scattered by others.
Yeah. So I mean, here, for example, in particular, we don't really need to worry about mean free path in the sense that we are really in a confined geometry, but nevertheless, we have to worry about the coherence time or the lifetime of the phonon.
Yeah,
so,
that's about the same, isn't it?
Yeah, that's the same. Yes, you're right. So that's why it's not been observed so far, as I can tell. The coherence time of the phonon is really short, so you have to pump faster than that, and that's really fast.
But
so,
there are some experiments with spin resonance, where also was pumping on a phonon bath, and it was carried out at very low temperatures, a frequency around 10 gigahertz, and there was clearly a phonon amplification visible.
Yes. Yeah, so I think at these frequencies, you can have much longer mean free path or coherence times. With molecules, there could still be modes. I mean, we could go at 4 Kelvin if it helps. I think that we can do.
Yeah, that would help, isn't it?
Yeah, so we have to work on it, and I think it would be interesting to have among this. If you look, but in DPT, it doesn't seem that there are very sharp modes, but definitely some are sharper than others. So if we find a mod that is, and that's something, for example, Diego, you have been also thinking about that. Can we find some mods which are much sharper, longer lived? And still also have good Raman cross section to drive them into oscillation. That's an open challenge to combine. I think the challenge is to combine this condensed matter environment of the plasmonic particles, the metal around, and the long coherence time of the phonon. So phonons with long coherence time has been evidenced in vacuum or on very crystalline surfaces like sodium chloride, things like that. There has been molecular spectroscopy showing that molecules can vibrate very long on this environment. Yeah. When you put them in plasmonic cavities, so I think there is really interesting works to be done in finding a trade-off where you can still get good plasmonic amplification and long vibrational lifetime, which remains an open question.
Okay, thank you.
And we have another question by Carlos. Carlos?
Yes, hello. Can you hear me?
Yes. Yeah.
Yeah, so I have a question about a comment that you said while discussing this transduction process. And I think you mentioned, okay, in order to see an anti-Stokes peak, we need to have some initial population of an excited vibronic state, right? Mm-hmm. But then you said that in your interpretation of this, you are not creating like a thermal occupation of this excited state. So I want to understand this better, because I mean, is it correct to at least think that in this transduction process, the mid-infrared drive will excite a phonon state, and then you will have the anti-Stokes process, or what is?
I think indeed that's the problem, is that this picture of sequential process, like you absorb an infrared photon, create a vibration, and then convert it to anti-Stokes, is that in fact it's wrong, at least in the regime where we are. It doesn't reproduce the spectrum. So you really have to think in terms of a frequency mixing process, like you would have in any other nonlinear optics experiments. So or actually, for that matter, the classical picture is more accurate. So if you think of a classical oscillator, if you drive it at some frequency, you will see that it's oscillating at this frequency and not any other. So the susceptibility will be following the spontaneous coherence of the oscillator. But once it's driven at the frequency of your pump with just some phase lag depending on where you are. And this now, you can imagine that you have your molecules which are each thermally excited a tiny bit. So this is this incoherent background of vibrations. And then you have on top of it this mid-infrared drive, which adds to them a coherent modulation. And this now is modulating your visible beam. So now you can think of like a lithium niobate modulator where you have some field oscillating at 10 gigahertz and creates two sideband at 10 gigahertz. So this is the same effect here.
Okay, so you mean if I want to understand this, I need like theoretically to go to like a semi-classical description, or like describing this vibrational mode as a complex number, no? As what you are plotting there, no? Like a displaced
I think
state.
if you look in the quadrature in continuous variable, then it's also easy to see. But if you really think in terms of discrete energy state, it's hard to
yeah, okay, yeah, I understand. Okay, yeah, thank you.
All right, then I think we're done. We thank Christophe.
Very interesting questions. You all followed very well.